Hi, Julia. It's me, Joe. Just wanted to say hi. Wish you a great day. Tell you that meeting you yesterday and getting a look at you was probably one of the greatest moments of my life.
Hey everyone, welcome back. So my name's Rob, and this is a course on introductory statistics for the psychological sciences. And today, we're going to be going through a full computational example of a one-way ANOVA from beginning to end, including all the computations, computing the Omnibus F-test, measures of effect size, conducting a planned comparison, and a post-hoc test, and then we're going to write it all up in APA style. So I'd encourage you to follow along with this lecture with a piece of paper and pen and a calculator yourself. Double check my work, and so if you find this video helpful, don't forget to like it and subscribe and click the notification bell so you get updates on future videos just like this one. So for now, let's just dive into the example problem. So today we're going to be looking at broadly the question, does social media use reduce self-esteem among female adolescents? So let's dive into the specifics of this problem. A social psychologist was interested in whether social media would cause reduced states of depression among high school females. She randomly selected a sample of 40 females attending high school in her state, and then randomly assigned each of the students to one of 4 experimental conditions: Facebook, Instagram, Snapchat, or no social media. Over the course of a 30-day period, the participants were required to use only their condition-specific type of social media. Additionally, participants were instructed to use their assigned social media platform for at least 1 hour per day and to make at least 1 public post per day. The primary a priori hypothesis was that participants who used any type of social media would have significantly lower self-esteem than those who did not use any social media. But the researcher also sought to explore whether these different social media platforms varied in their influence on self-esteem. Okay, so the raw data is presented on the next slide. So, here we can see we're measuring self-esteem among female high school students, and this represents their self-esteem score. So these measures were taken using the Rosenberg self-esteem scale, which is a scale from 1 to 4, and there's a total of 10 items. So the maximum score that you can receive on this self-esteem measure is 40. A score of 40 would mean that you had extraordinarily high self-esteem. And the lowest score that you can obtain on this is a 10, which would mean that you had very, very poor self-esteem. Well, we know that people tend to be relatively high on self-esteem, at least as measured by self-report. And this data is consistent with that. You can see that most of the values range between the 20s and the 30s. Okay, so let's go through step by step how we are going to approach this problem. So we need to determine what the appropriate statistical test is. Now, in this case, we have an independent variable with 4 levels, right? 1 independent variable, you could say social media type, and we've got the Facebook level, the Instagram level, the Snapchat level, and the no social media level. And what we're measuring is an interval or ratio variable, which is self-esteem. And since we have a 4-level independent variable and a quantitative dependent variable, we know this is going to be an ANOVA. So the next step is we need to determine, is this a between subjects or is this a repeated measures design? So we determine that. We can see that the high school students were randomly selected and then randomly assigned, each to one group. So one group of people is going to consist of people using Facebook, and then another group is going to consist of different people using Instagram, and so on with Snapchat and no social media. So because there are different people in each level of the independent variable, this is a between subjects design. So we know that we're going to be using a one-way between subjects ANOVA. Okay, so we'll put that down for our response for number 1. Okay, now we can move to number 2, which is setting up the hypotheses. So, to the null hypothesis for this, again, remember that we're looking at an omnibus test here. So what the question we're trying to answer with the one-way ANOVA test is, for this omnibus portion, do any of the groups differ from any of the other groups? So the null hypothesis is that all the groups are going to be the same. So I'm going to say mu of Facebook is equal to mu of Instagram is equal to mu of Snapchat is equal to mu of no social media. The alternative hypothesis is going to be that at least one group is different from at least one other group. So the null hypothesis is going to be all group means are not equal. Okay, and now we can move to the third step, which is determining the critical value of f. So to determine the critical value of f, we must first know what our degrees of freedom are. And so we'll look at this ANOVA summary table. We'll be reviewing the ANOVA summary table over and over throughout this problem. It's a good way to organize the information that you compute. So our degrees of freedom between are k minus 1. Now remember, k in ANOVA represents the number of cells that we have. Well, we have 4 different groups, 4 different cells. So degrees of freedom is 4 minus 1, which is equal to 3. And degrees of freedom within is equal to the total number of people in the study minus the total number of groups, right? So total number of people in the study, there's 4 groups of 10 people. So that's 40 people minus 4 groups. So degrees of freedom within is going to be 40 minus 4 is 36. So degrees of freedom is going to be 336. Now, it's a good practice to just go ahead and put that information into your table. So here we have 3 degrees of freedom between, 36 degrees of freedom within, and then we should add it up to get our degrees of freedom total, which is 39. Now, we can double check our work because we know that degrees of freedom total is equal to big N minus 1. So this should be 39. So if our numbers, if 3 plus 36 is 39, it is, we know that we're on the right track. If you don't find, if your degrees of freedom between and degrees of freedom within do not add up to N minus 1, something went wrong. You'll want to check that, because this computation is going to have implications for every single step that follows this. Okay, so the next thing we need to do to find the critical value is to use these degrees of freedom to locate this critical value in the table for f. So the top columns represent the degrees of freedom between, and the rows going down represent degrees of freedom within. So we have 3 degrees of freedom between. So we look at row 3 or column 3. And then our degrees of freedom within was 36, but 36 does not appear in this table. Whenever that happens, you always go up to the next lowest number. This is a conservative approach. But you go up to the next lowest number, which is 30, and so we can see that T crit is equal to 2.92. Okay, so then after this, we need to set our decision rule. We're going to reject the null if f obtained is greater than or equal to 2.92. Okay, the next step, and this is going to be a bigger step, is to compute the obtained value of f. So, this is going to be part 5. So how do we do this? Well, first we need to calculate the sum of squares between. And this is the equation to compute it. The next step is we need to look at our data and plug in these values. So we get sum of squares between is equal to 299 squared over 10 plus 270 squared over 10 plus 321 squared over 10 plus 348 squared over 10. And I'm going to fix this one because it could easily be confused. Okay. And then we need to subtract the sum of all x-scores squared divided by all of the people in the study. So this is going to be 1238 squared. You can see I have that number totaled all the way onto the right, divided by 40. So this gives us 89401 over 10 plus 72900 over 10 plus 103041 over 10 plus 121104 over 10 minus 1,532,644 over 40. And this reduces down to 8940.1 plus 7290 plus 10304.1 plus 12110.4 minus 38316.1. Okay, and then finally, we get sum of squares between is equal to 38644.6 minus 38316.1, which is equal to 328.5. So that is our sum of squares between value. Now after this, we want to plug this into our ANOVA summary table. So we've got sum of squares between. The next thing we need to do is compute our within group sum of squares within. So sum of squares within, this is the formula for it. So we're going to take the sum of all x squared scores and then subtract from that the same sum of squares values that we worked out in parentheses above or earlier. So let's plug those values in. So the sum of x squared we basically need to add up the squared columns. It's going to be 9177 plus 7516 plus 10,615 plus 12174. And then we minus this from the precise values that we resolved for earlier, which is right here, right? That's just all of these sum of x squared values for each group. So 38644.6. Okay, so let's compute this out. This is equal to 39482 minus 38644.6, which is 837.4. Okay, so that is our sum of squares within value. And of course, the next step is going to be to add that to your ANOVA table. Now, the sum of squares between and the sum of squares within, when you add them up, you should get sum of squares total. However, to double check yourself, you should always compute sum of squares total using the formula. So to compute that formula, we have the sum of all scores of x squared, which we just computed, and then we subtract the sum of x of all scores squared divided by n. So let's look at sum of squares total. So sum of squares total is going to be the sum of all x squared scores, which we just computed. It is this value right here, 39482, minus the sum of all x values, which we computed in sum of squares between. And so that value was 38316.1. You can find that right here. Okay, and so sum of squares total is equal to 1165.9. So this is what we got whenever we did the computation of this. Now let's add up the scores that were in our ANOVA table and see if it matches. So 328.5 plus 837.4 is equal to, what do you know, 1165.9. So this is a very important step to make sure that these variables match. if you get the degrees of freedom incorrectly or the sum of squares incorrectly, this is going to cascade and make errors throughout the remainder of the table. So both of those values you can double check. With sum of squares total, you can add it up in the columns, and you can also use the formula to check it. And with degrees of freedom, you can add up between and within, and that should be equivalent to n minus 1. Okay, so now we have sum of squares total complete. And so the next thing that we want to do is we want to compute our mean square estimates. So the mean square represents the estimate of the population variance explained, and the mean square within represents our estimate of the population variance that's unexplained. So to do this, we simply plug in to the formula on the table. It's sum for mean square between is simply sum of squares between divided by sum of squares total. So mean square between is equal to 328.5 divided by 3, which is 109.5. And mean square within is equal to 837.4 divided by 36, which is 23.26. So again, you're just taking the sum of squares and dividing it by its respective degrees of freedom value to get the mean square values. And then we simply, the F ratio is a ratio between our estimate of the population explained variance, that is the estimate of the variance explained by the independent variable, and then the within is our estimate of the variance that remains unexplained by the independent variable. So F is simply a ratio between those two measures, two estimates of population variance. And so we just plug it in, and F obtained is going to be equal to 109.5 divided by 23.26, which is equal to 4.71, which is what we have here. Okay, now the next step is going to be to compute our measures of effect size. So we only really need to compute one. Remember, we can use either omega squared or eta squared. So just starting with eta squared. So eta squared is simply the sum of squares between over the sum of squares total. It's what proportion, it represents what proportion of the independent variable or of the dependent variable is explained by the independent variable. So in this specific case, what we're computing with eta squared is the percentage of variance explained in high school girls' self-esteem by their different levels of social media use. So omega squared is a slightly more complex computation, but it is a more accurate estimate of the true effect size. So let's start out computing omega squared. So omega squared is equal to 328.5, which is our sum of squares between value, minus k minus 1, which is really just degrees of freedom, times the mean square within value, 23.26, over the sum of squares total, which was 1165.9, plus 23.26. And this is going to break down into 328.5 minus 69.78 over 1189.16. And this gives us an omega squared value of 0.2175. So again, this is omega squared is a more conservative measure of effect size. And what this means is that 21.75% of the variance in self-esteem is explained by social media type. Now let's go ahead and just run through the eta squared equation. So eta squared is going to be sum of squares between over sum of squares total. And so that is 328.5 divided by 1165.9, and this gives us a value of 0.2817. And here you can see both of these effect sizes mean the same thing. However, eta squared is often biased upwards. It's too large. It's an inflated measure of effect size. So omega squared kind of controls for that inflation by taking into account degrees of freedom. Okay, so which one's right? Well, you could use either one. You're going to interpret them the same way. So here at the bottom, you can see the cutoffs to interpret it. And this is, in both cases, would be considered a large effect size. Okay. The next thing that we need to do is determine whether or not we reject or fail to reject the null hypothesis based on the decision rule. Well, so our decision rule, we'll scroll back up here, was reject the null if f obtained is greater than or equal to 2.92. So for part 6, 4.71 is greater than 2.92, so we reject the null. So this is, when this happens with real world research, this is a very big point of excitement. Okay, but keep in mind that what this significant F is telling us is that at least one group is significantly different from at least one other group. It's not telling us that all the groups are different or which groups are different. And so in order to determine that, we need to do either planned comparison or post-hoc tests. So it's very important to understand that a significant F means that you need to investigate further. If it was not a significant F, we would completely skip step 7. We would not need to do those. In some cases you could, if you have an a priori hypothesis. Sometimes it's not even necessary to conduct an omnibus F test. But in this case, we do have a specific hypothesis. We also had some exploratory questions. So we're going to need to do planned comparisons and post-hoc tests. So let's go back and look. So if we have an a priori hypothesis, we're going to need to do a planned comparison. So here was our original problem. And in this highlighted section, it says her a priori hypothesis was that participants who used any type of social media would have significantly lower self-esteem than those who did not use any social media. Okay, so we want to compare any type of social media use to people who don't use social media. So we had a significant omnibus test. Even if it was not significant, if you have an a priori hypothesis, it's okay to go and do a planned comparison test afterwards. Our F was significant, so we're going to, either way, we would still do this test. But, okay, so we are going to go through the steps of doing this planned comparison, and essentially, it's just a t-test, right? So we're going to set our hypotheses, right? Our null hypothesis is that social media is equal to no social media, and our null hypothesis is that the population mean of all people who used social media is going to lead to lower self-esteem than the population of people who do not use social media. Then we need to find the t-critical value. So to do this, when you're doing a planned comparison, you're going to use the degrees of freedom within for your ANOVA. And you're always going to look at a one-tailed test. And in this case, alpha is 0.05 because it wasn't specified. So we go to our t-table, alpha of 0.05 in the alpha of 0.05 column. And then our degrees of freedom were 36. But again, since we want to be conservative here, if we have a number that's over 30 and under 40, we're going to go back up to the numerically lowest number in the table. So we're going to go to 30. And our t-critical value is going to be 1.697. Okay. Our next step, we're just going to set our decision rule. We're going to reject the null hypothesis if t obtained is greater than or equal to the t-critical value of 1.697. And then we are going to compute our t obtained value. And here is the equation for t obtained. So let's go back and look at our data here. So we've got 3 groups that are all going to be balled together into one group containing them all. So our x bar 1 is going to be the mean of all of the groups who use social media. So it is essentially 29.9 plus 27 plus 32.1 divided by 3 minus the mean of the second group, which is the no social media group. So it's 34.8. And then all of this is then divided by the square root of mean square within, 23.26, times 1 over the sample size of group 1, which was 30 because there's 3 groups, plus 1 over 10. And so this is going to resolve to 29.67 minus 34.8 over the square root of 23.26 times 0.13, which is equal to minus 5.13 over 1.74, which is equal to 2.95. So our t obtained value is 2.95. We need to go back now and determine whether or not we reject or fail to reject. Well, we just compare. Is our t obtained value of 2.9 greater than 1.697? Yes, it is. So we reject the null hypothesis. And basically what this means is that people who used any form of social media had significantly lower self-esteem compared to people who did not use social media. Now, one important thing I want to point out is, so Sometimes when we're setting up this t equation, people will say that you should have the biggest number first minus the smallest number. Another way to do this is just to say it's the absolute value, right? And the key here is we don't want to take directionality into effect. So the negative sign goes away, right? We're just looking at the difference, the magnitude of the difference. We don't need to know the direction when we're doing this plan comparison. Okay, now post hoc comparisons. Well, so we had a significant plan comparison. We know that using social media has a negative impact on the self-esteem of high school females. And that was our a priori hypothesis, the hypothesis that we had predicted in advance. However, we also had an exploratory question. Our exploratory question was that the researchers sought to explore whether the different social media platforms varied in their influence on self-esteem. Now, she didn't have a specific hypothesis. She didn't think that Facebook would be higher than Instagram or higher than Snapchat. She just wants to explore the data and see if anything comes out that would be informative for future research. Now, the very important point here is when you conduct a post hoc test like this, you should never, ever claim that you predicted something a priori, that you had a hypothesis in advance if you're doing a post hoc test. This is intended for pure exploratory research where the a priori plan comparison that we conducted is designed to allow us to assess a very specific comparison that we anticipate in advance, even in advance of collecting the data. The post hoc is when we want the data to teach us, right? Where we want the data to inform our understanding of how social media affects self-esteem. We don't really know. And then we can use what we learn from this to conduct future studies examining the different social media platforms. And at that point, we could create a new a priori hypothesis to test. So when we have an exploratory question and we don't have a pre-specified a priori hypothesis, we're going to do what's called a post hoc test. Now, post hoc tests are not theory-driven. And since we're running basically every possible comparison between the means, we have to correct for the family-wise error of conducting that many tests. That's what post hoc tests are designed to do. They're designed to maintain the type 1 error rate at a pre-specified alpha level. In this case, the alpha is 0.05. So there's a variety of different types of post hoc tests. There's the Tukey honestly significant difference test. This is probably the most common form of post hoc test that people conduct. There's also the Scheffe's test, which is a bit more conservative, meaning it makes it slightly more challenging to reach significance. It constrains the type 1 error rate a little more. There's also the least significant difference test. There's a whole host of them. But today we're going to go over the Tukey honestly significant difference test. And basically, it's similar to a t-test, except now we're in the realm of Q. We need to determine a critical value of Q. We set the decision rule, which is going to be, if Q obtained is greater than Q critical, then we reject the null. And then we calculate Q obtained for all possible comparisons. So let's look at this Q table. So this are the critical values for the Tukey test. And so one thing that is very easy to mess up here is Remember in the F table, the top row was K minus 1, the degrees of freedom. More specifically, the degrees of freedom between, or the degrees of freedom in the numerator of the F equation. But in the Q table, it's asking you for the number of groups, which is not K minus 1, it is K. So in this instance, we have 4 groups. So we want to use column 4. And then for our error degrees of freedom, that is just our degrees of freedom for within, right? Our unexplained variance or error variance. We're going to use the degrees of freedom of 36. Again, we don't have a 36 on the chart, so to be conservative, we use the next appearing numerically lowest number, which is 30. And we get a critical value of Q of 3.85. Okay, so next our decision rule is going to be to reject the null if a Q obtained value is greater than 3.85. And we need to compute Q obtained for all possible comparisons. Now I'm going to try to demonstrate a relatively quick way to do this, because these can get kind of gnarly whenever you have more than 4 groups especially. There's so many different comparisons. So first we should compute the denominator of the Q obtained value. Which is the square root of mean square within, which is 23.26, divided by the size of the groups. So in this case, it's n. Okay. Next, or I'm sorry, not n, 10. Okay, and this computes out to be 1.5251. So again, this is just the denominator of the Q equation. The next thing we need to do is we need to take the absolute value of the difference between one group and another group. Now here, the formula says put the larger group first and the smaller group second. That's one way to do it. I find it easier, rather than fiddling with which one's larger or smaller, to just take the absolute value. In other words, drop the sign. We're looking at the magnitude of the difference between these means, not the direction. So we are going to have Facebook versus Instagram, Facebook versus Snapchat, Facebook versus no social media, Instagram versus Snapchat, Instagram versus no social media, and Snapchat versus no social media. And then what we need to do is go look back at our table and just plug in the means. So Facebook versus Instagram is going to be 29.9 minus 27. Facebook minus Snapchat is going to be 29.9 minus 32.1. So we can go down now. A quick way to do this is anytime you see an F here, you just put 29.9. And anytime you see an I, you put 27. And anytime you see an S, you put 32.1. And we didn't get N yet, but N is 34.8. Okay. And now we just take these differences we have 2.9, 2.2, 4.9, 5.1, 7.8, and 2.7. And we divide these differences by 1.5251. And we get our obtained values of Q. Okay, so now that we have our obtained values of Q, we're going to basically run our decision rule by each one. And our decision rule was reject the null if Q obtained is greater than or equal to 3.85. So this is not, that's fail to reject, fail to reject, fail to reject. So far, none of them are greater than 3.85. Oh, here's one. And fail to reject. So I have this summarized on the next slide. And we can see that, none of the comparisons were significantly different except for Instagram versus no social media. And what this means is that in this exploratory way, we're demonstrating that Instagram had led to significantly lower levels of self-esteem among high school females compared to those who did not use social media. But none of the other conditions were significant. So what we need to do at this point is write the results up in an APA-style format. So to write it up in APA style, we're going to need to have a lot of the numbers that we calculated ready to go. So I'm going to scroll back up to the top of our problem here. And the first thing we do, again, we're following the same format we did with an APA style results section for the t-tests. However, we start getting into a little bit of nesting because we're doing multiple different types of tests. So the first thing we want to start out with is what did you do for the Omnibus test? So we want to say a one-way between subjects ANOVA was conducted to assess 1 month of daily social media use and its effect on reducing the self-esteem of female high school students. Then for what did you find, right? So obviously the key piece of information that you need to write that what did you do is the one-way between subjects ANOVA. What did you find? We say the Omnibus test was significant. And the reason we say that is because we rejected the null hypothesis. If we come back down, you can see we rejected the null. That means it was significant. And what it indicates is that at least one type of social media use was significantly different from another in its effect on self-esteem. And then we report our F obtained value. But we report the degrees of freedom between, degrees of freedom within. So we can go back up and we can see we created our degrees of freedom between and within. So we report F 336 is equal to our F obtained value, which our F obtained value was 4.71. Because it was significant, the probability that this result is due to a type 1 error is less than 5%. We want that to be less than 5%. We want it to be unlikely that this is due to error. So our error rate less than 5%, or our alpha value, p is less than 0.05. If it was significant, it would be p is greater than 0.05. And then we report our effect size. Now we could report omega squared or eta squared. Typically, eta squared seems to be more common in the published literature. However, omega squared is definitely gaining in popularity, and it's certainly an effect size measure that is more robust and more conservative than a eta squared. So I reported the omega squared here, and we got that. We had omega squared is 0.2175, and so you round to 2 decimal points in APA style. And then we interpreted it. When we computed that, we determined it was a large effect. And then you explain what that effect size means, right? And so that means that social media type explained 22% of the variance in self-esteem. Okay, so for the next part, then we need to go in, and so this Omnibus test gave us confirmation that we need to investigate more. So we did a planned comparison first. And we say, to test our a priori hypothesis that using social media would negatively impact the self-esteem of high school females, a planned comparison was conducted, testing the effect of using Facebook, Instagram, and Snapchat against no social media use. Then we say what we found. Results from this comparison indicated that compared to those who did not use social media, and then we report the mean that we computed to compute our t-value, which if we look here on our t-crit equation, the mean was 34.8 for people who did not use social media. And then we were comparing them to students who were required to use social media for 1 month. So that was all 3 of the social media groups. And we report that mean and how many people were in that mean. And then we indicate, that they were lower on self-esteem, and we report our t-value with the degrees of freedom for degrees of freedom within. That's what we used to look up the critical value. That's how many degrees of freedom were in this test. And then we report our t-obtained score. And p is less than 0.05. Now, technically, you should also report a Cohen's d value and a confidence interval. But I didn't want to make this video that long. So the next thing is we interpret this. We interpret this for a person. This is the headline. What someone who does not understand statistics, what does this mean for them? Right? And so this suggests that social media use has a dramatic negative effect on the self-esteem of high school female students. Then we need to write up our post-hoc tests. I apologize, I have planned comparison on the slide. And so for our post-hoc Tukey tests, we say to explore whether the daily use of Facebook, Instagram, or Snapchat were different in their impact on self-esteem. We conducted a post-hoc Tukey test to assess whether there were differences between group means. The post-hoc comparisons revealed that Instagram, and then we report the mean for Instagram, led to significant decreases in self-esteem compared to no social media use. And we report the mean for no social media use. There was not sufficient evidence to conclude that Facebook and the mean, or Snapchat and the mean, negatively affected self-esteem relative to no social media use. And none of the social media platforms were significantly different in their impact on self-esteem. One key thing, this is an opportunity for you to really wrap your mind around what emerged from those post-hoc comparisons and concisely figure out what it means when you put it all together. You don't want to say, Facebook was not different from Instagram. Facebook was not different from Snapchat. Facebook was not different from no social media. Instagram was not different from Snapchat. You don't want to go through like a robot. You want to use your writing ability and your intellect to really think through what the results indicate and report that as specifically and concisely as possible. Now, one thing is you do want to report all of the group means in this write-up. Alternatively, if you don't want to report them in the write-up, you could create an APA-style table showing the means. And then we interpret what the post-hoc test means. So this suggests that daily Instagram use had deleterious consequences for the self-esteem of high school females as compared to no social media use. And then we write up the overall summary of what it means. We say, in conclusion, it appears that social media use can negatively impact the self-esteem of high school females. Of the 3 social media platforms tested, evidence emerged that Instagram was the only social media platform that elicited substantial negative consequences for self-esteem. On the basis of this research, parents would be wise to monitor the daily use of Instagram. Future research should examine the boundary conditions for daily use to determine how much social media use is needed to impact self-esteem. So obviously this could take a variety of forms, but you want to summarize what is the important thing that people should learn from this research and from from everything, your planned comparisons and your post-hoc. And then here is the full APA style write-up all on one page. As you can see, these have grown quite a bit since the good old days of one sample t-tests. But they follow the same pattern. For the most part, this is not the type of writing where you should be trying to express your creativity. This is quite a structured format of writing, and I encourage you to use this as a model should you have to write up the results of a one-way ANOVA for this class or for your subsequent research. Okay, so that is the end of this one-way ANOVA example. I hope this was helpful for you. If you have any questions, don't forget to leave them in the comment sections below. And if you like the video, make sure you hit that thumbs up and don't forget to subscribe so that you can get videos like this in your feed, and hit the notification bell so you're notified whenever I release new videos in the realm of psychological science. Okay, thank you. I hope you have a good day.
So, open up your heart to me and your arms. Let's go full throttle. I could see me falling in love with you. I don't know, I just looked in your eyes and I just melted. Anyhow, I'm heading off to work.